Hi everyone, in this lecture we are going to discuss the last topic in module 4, which is related to distributed force. In module 2 we have known these terms when we discuss the type of forces, which is based on distributions. Forces can be divided into point load and distributed force. Okay, and if we could further categorize this distributed force, it can be further divided into three categories. The first one is a line distributed force, and then the second is the area distributed force, and then the third is a volume distributed force. Okay, and in here for the line distributed force, it will have a unit of force divided by length. Okay, for the area distributed force, it will have a unit of force divided by length square. Okay, and the volume distributed force, it will have a unit of force divided by length cube. Okay, and in this course, most of the case we will discuss problems that are related to line distributed force. Okay, so however there might be few problems where we will use the area distributed of the volume distributed force. Okay, but most of the time we will try to solve problems that involve line distributed force. Okay, and when the problems involve the area and volumes, with the knowledge that you have for the line distributed force, you should be able to solve that as well. Okay, so let's get started. Let's assume I have a beam and I have distributed force with functions of Wx describes how the force are distributed. Okay, and in here we have point A and point B, right? And then we measure our x from point A to the right. Okay, and then let's assume that the length of the beam is L. Okay, so the main objective when we try to calculate a line distributed force in here is how we can include it to calculate the external effects. Okay, so what is external effects? So basically external effects is like a reaction forces that we will discuss in depth later in module 5. Okay, to calculate the external effects, we can further simplify this distributed force into its resultant force. Okay, and let's call that resultant force is R, that is located at a distance x bar from the end of the beam. Okay, and in this case I choose that I define x bar from point A, which is the left hand side of the beam. Okay, so in here you can see what is the reasons why we put this topic in module 4, because we are most likely interested in finding what is R and what is x bar. Okay, and we can say that these two systems, system 1 and system 2, okay, they are basically an equivalent systems. And we have learned from previous lectures in module 4, when we have an equivalent systems, no matter which system that we choose, when we try to calculate the external effect, it will give us the same result. Okay, and what I mean by external effects in here, as I mentioned earlier, is the reaction forces, okay, that we will discuss in depth in module 5. Okay, so let's formulate two equations on how we can calculate R and X bar in here. Okay, so if I take a section right here, okay, if I take a section right there and I call that in here is dx, okay, and the distance from point A to this bar right there is x, okay, so I can calculate my dr, which is the resultance of this small section right here, is wx times dx, right? So it's basically the area of a rectangular with a width of dx and height of wx. Okay, since this is only for a small section dx right here, meanwhile we are trying to calculate the resultant force for the entire distributed force in here, we need to perform the integration. Okay, when I integrate this left hand side equations, I obtain r, and this right hand side equations is integral of wx dx from 0 to L, because in here we try to integrate for the entire length of the beam. Okay, so this is the first formula that will be very useful, which is the resultant force is the integrations of the distributed force over the length of the beam. Okay, and in here basically this integration means it is the area under wx, right? So we basically the area under the distributed force right there. Okay, the next is questions that I would like to formulate is to calculate this x bar right here, and to calculate to formulate that expressions, I would like to calculate sum of moment about point A from this first systems and the second systems right here. Okay, because they are equivalent system, sum of the moment at A should be the same. Okay, so let me consider the first systems right here. Okay, so sum of the moment at A, so system 1 is equals to, we already know what is dr right here, right? And we know the distance of dr to A is x. Okay, so I can first calculate dma. Okay, so dma is x times dr. Okay, and really in here we have negative sign. Okay, since this differential moment is just a contribution of dr, meanwhile we are interested in finding the contribution of moment from the entire distributed force, then we will need to perform the integration. Okay, integrating the left hand side equations, I obtain ma. Okay, and then the right hand side equations becomes x. Okay, and dr, we know dr is wx dx, right, from what we have formulated in here. Okay, so in here I obtain that my m of A is x wx dx. So basically sum of moment at A is just m of A is x wx dx. Okay, so that's from system 1, and right now I'm going to formulate it from the system 2, and it should be much easier. So this is system 2, right? So sum of the moment at A will be just minus r times x bar, right? minus r times x bar. So since these two systems are equivalent systems, then we will expect that the sum of moment from these two systems are going to be the same. So in here I can write it down as minus r x bar is equal to minus x wx dx. Okay, so I can take out the negative sign, right? And then I can calculate my x bar as integration of x wx dx divided by r. Okay, and I know the r is integration of wx dx, and in here we perform the integration from 0 to L and 0 to L. Okay, and this is the second formula that is very helpful. All right. Okay, I would like to encourage you to perform calculations to find what is r and x bar for a simple distribution of distributed force. So let's say that we have a beam, right? The length of the beam is L, okay, and we have a uniform distributed force in here, and let's call that Wx is W naught. So the W naught is basically the intensity right here, okay, and I would like you to calculate what is the resultant force R, okay, and then what is x bar, okay, alright, and express your result in here in terms of W naught and L. Okay, so please give it a try. Meanwhile, the next things that I'm going to show you, so instead of having a uniform distributed force, sometimes I may ask problems where the distributed force is not uniformly distributed, but rather is distributed through some functions. For example, here we have a triangle distributed load with peak at right end. Okay, so the peak is at the right end of the beam, and the peak in here, the intensity is W naught. Okay, so in here the intensity is W naught, and in here the intensity is 0. So if you ask me what is the function that define this linear line in here, is described as written in here. Okay, and I have pre-calculated everything for you in here, and this is how you do the calculations for R, and this is how you obtain x bar from the left hand side and x bar from the right hand side. Okay, and basically this is the two equivalent system, right, where the R is W naught L over 2, right, and XL is 2L over 3 and XR is L over 3. So if you try to analyze in here, the resultant force is like an area of a triangle, right? So basically area of this triangle right here, right, is 1/2 W naught times L, where this is the height of the triangle L, and this is the width of the triangle W naught. Okay, a similar result you will obtain if I mirror the distributed force. So right now the peak is located at the left hand side of the left end of the beam instead at the right end. Okay, so this is the function that describes the distribution of the distributed force, and you will obtain that R is still the area of the triangle W naught L over 2, but however in here XL is L over 3 and XR is 2L over 3. So you can observe from this first case in here, case 1A and case 1B, that the resultant force R is closer to the end of the beam with the highest intensity. Okay, so in here, if the W naught is located at the right end, R is closer to the right end. Okay, you can see from here and here. Okay, and if the highest intensity is at the left end, R is located closer to the left end, as you can see from XL and XR in here. Okay, similar result if right now we observe case 2A. Okay, it's a second order distributed force. Okay, and in here the distributed force is distributed using this function. Okay, then you will obtain an equivalent systems. This is the R, right? This is the X bar from the left hand side. This is the X bar from the right hand side. Okay, and this is the calculations how you obtain R and XL and XR. Okay, so in the case 2B, right now the highest intensity is located on the on the left end instead of right end, and this is a function that describes the distribution of the forces. Okay, and if you perform the calculation, you obtain R is this. Okay, W naught L over 3. Then this is X bar from the left end, and this is X bar from the right end. Okay, and then the last case in here is still a second order curve, but instead of having a concave curve, right now we have a convex, right? So if I'm not mistaken, we call this convex, but please double check. Okay, so in here the distribution of the force Fx is distributed using this function, right? Then we can calculate the R. Okay, following the same process as before, we obtain 2 over 3 W naught times L. Okay, then we obtain X bar from the left hand side and X bar from the right hand side. Okay, and then if the intensity right now is in the left hand side instead of at the right end, based on this function, right? Okay, still a second order curve. Okay, we obtain that R is the same as before in here, and XL, XR is obtained using the same process as before. Okay, alright, I think that's it for this lecture. Thank you for listening. If you have any questions, please don't hesitate to let me know, right?